All right, now let's start today's lecture. So in today's lecture, we're going to introduce an example of using a PySpark machine learning library to implement a naive Bayes classifier. And during that, we will also introduce the pipeline, which is a very important and useful tool when you build when you implement a classifier or machine learning, implement a machine learning task. We will also show some commonly used operations on data frames when you do a machine learning job, and after that we will introduce a machine learning framework called stacking, where this would be used in project 2. So today's lecture is very important for project 2. We will explain what to do in project 2 in very detail. All right. So now let's look at the example. All right. So on Monday's lecture, we have introduced naive Bayes classifier. We have also introduced a little bit about the PySpark machine learning library. So now let's look at an example of using machine learning library to implement a naive Bayes classifier. So the first step would be create a Spark session and read data. Right. So here we show another way of reading data. Another format, right? Which is CSV. Right. So the file, this is the CSV file. So the CSV file would looks like the following. So the first line or the first row is the header. So the header is category and description. So the category would be MISC or REST, REST for restaurant. This is the CSV file that we will use in lab 3. So I just borrow it here. The description is basically a sentence or a couple of sentences. So just a document or a sentence. And all right, so we kind of need to read in train data and development data. Here the format is CSV, and this is the separator in a CSV file. So means here is actually a tab. You can also use a space, a white space, or a comma as a separator. It is defined by you, but just make sure that the separator that you have defined here is consistent with the one that you're using in the CSV file. And infer schema means you ask Spark to inference the schema of the CSV file. And header is whether the CSV file contains a header or not. So here the CSV file actually contains the header, but if it does not, and here you assign true to header, then it would take MISC and this whole sentence as the header of the CSV file or the data frame. So be aware that this one, the header and the separator must be consistent with the CSV file. So this is what the file is, and this is when you show the first 5 rows, you can get. So these are what you can get. All right. Then the second thing after we have read in the data, the second thing is to build a pipeline. So this is the example of building a pipeline. We will look at this later. So let's firstly introduce or discuss what is a pipeline. So in machine learning, it is common to run a sequence of algorithms or procedures to process and learn from data. So for example, a text document processing workflow, for example, may include several stages or several steps. For example, you need to split each document, the text in each document into words, and then you need to convert the word into a numerical feature vector for each document. And then you probably want to learn a prediction model using the feature vectors, which you have converted just before, and the labels. So here, as you can see, there are two things. One is process data and one is learn from data. So that is usually the two main purpose or main operations in a pipeline. So a formal definition would be that a pipeline is specified as a sequence of stages. So this stage is not the stage in RDD, or some of you have been struggled with in the assignment. There are different concepts, just happens to have the same name. So each stage in a pipeline is either a transformer or an estimator. We will introduce what is a transformer and what is an estimator later. But for now, you just know that the stage are either a transformer or an estimator. So the stages are run in order. That's why it is a sequence of stages or algorithms. And the input data frame is transformed as it passes through each stage. So here, the very important thing is that the input of a pipeline has to be a data frame. In that way, the PySpark machine learning library has a strong connection with the PySpark SQL through this data frame. So you should always remember the input is a data frame. Now let's look at what is a transformer. So the transformer stage is called on the data frame, and it will generate a data frame. So basically the input and output are both data frames. And the estimator, on the other hand, it has two methods. It has two methods. One is fit, one is transform. You have to call the fit method first, so that such that it will produce a transformer, and the transformer will become part of the pipeline model or the fitted pipeline, and the transformer has a transform method, so just like the transform method here. So it takes a data frame as input and output a data frame as well. So the transformer stage actually corresponds to processing data. So this is processing data, and the estimator stage, as you may expect, it actually corresponds to learn from data. But it is not only learn from data, So learn from data is more like what fit does, but it also predicts on data. So that is what transform does. Again, it may be a little bit dry, so let's look at an example here. So we should look at the code first. Now, in order to build the pipeline, as you can see, we build the pipeline here at the last step. So the pipeline contains a word tokenizer, a count vector, a label string index, and a naive Bayes model. So let's look at them one by one. The word tokenizer, right? So it's just a tokenizer using a white space as the splitter. All right. This is by default. I mean, you by default it use white space as the splitter. So in order to define such a transformer, so this is a transformer. We will see it later. You need to specify the input column and the output column. Now, if you still remember, the data looks like, the train data only have category and descript, only have these two columns. So we use the input column, which is descript, and we define the output column. So you can imagine after this transformer, it will produce a data frame with additional column called words. So it should be something like you would have a words here, and the words would be like a list. So being there, something like this. All right. So this is what the word tokenizer does. Then we use a bag of words count, or the count vectorizer, as the second transformer. So it is still a transformer. Again, we need to specify the input column, which is words, which is the output column of its previous transformer. But it does not have to be, I mean, its previous, the output column of the previous transformer. It just happens to be the same here, or usually, because it is a pipeline. So usually the input column should be the output column of its previous transformer. All right. Then the output column is defined is named as features. So it will count the bag of words which we have introduced in Monday's lecture. So essentially, it is the frequency of each and every word in the vocabulary, in the sentence. Sorry, in the sentence. So it will generate a vector, but in PySpark, it will actually generate a sparse vector. Yeah, as this is Monday's lecture. Sorry, this has been discussed in Monday's lecture, but the features here is actually generated by that count vectorizer. So this is a sparse. This is a sparse vector, right? So 5,421. This is actually the number of words, or the size of vocabulary. Right. since it has been converted into a feature vector, the word itself does not matter, right? Does not matter. So here indicates the length of the vector, and each number here, for example, 1 means the first word in the sentence. And 18 is actually response to the 18 means the 18th word in the sentence. And here, because it only printed out part of the feature vectors, so actually the feature vectors would looks like there is another list here, because it is a sparse vector. So this list contains the counter, the count of each word in the previous list. For example, 1.0, 2.0 means the first word, the frequency is 1. The frequency of the 18th word is 2. All right. So this is how the feature vectors looks like. So then you can, it is straightforward or easy to see that the length of this list and this list would be the same, and the total length would be the same, and the number are both 5,421. Now let's go back to here again. This is what the count vectorizer does. And yeah, we have defined the input column and output column. The third transformer would be the label indexer. So the label indexer, what it does is that it takes the input column, that is category, and outputs the column called named label. What it does is essentially do a string indexer, because here, as you can see, the category, which is essentially the label of each sentence, it contains strings. But in MLlib, we want the labels to be numbers, right? So using this transformer, it will generate a new column called label, and the value would be, for example, 1.0 for the first, fourth, and fifth row, and 0.0 for the rest two rows. This is essentially what the string indexer does. And as you can see, in this transformer, the input column is no longer the output column of previous transformers. It is actually a column in the original or the row data frame. And with these three transformers, the last one would be an estimator. Right. So this estimator is essentially a naive Bayes model, because the estimator is meant to we use the estimator to learn from data. So it should be or usually be a classifier or a model. Right. So the parameters for a estimator is different from the parameters of a transformer. As you can see, for transformer, we need input column and output column, but for estimator, we need to specify the features column, label column, and prediction column. So essentially, the features column is the feature vectors. It's the column of feature vectors. The label column is the column of label. So these two should be already in the data, in the data frame. The data frame. And for the prediction column, this column is to store the prediction result. So this column would be a new column when we call later you will see when we call a transform method of the pipeline model, it will add this column to the data frame. Then the last step would be build the pipeline. So it is kind of easy. You just call a pipeline with a defined stages, where the stages would be a list of transformers and estimators. But just remember that the order here matters because it is a sequence of procedures or algorithms. So the the order in this stage matters. You can imagine if you switch the order of word tokenizer and count vectors, then the input column of count vectors, you don't have it in the original data frame. Right? That's why you need to do a word tokenizer first. But on the other hand, I mean, you can put, so this is not allowed, but you can actually put label string index as the first step or the first stage in the pipeline, because the input column is in the raw data frame. It's not the output column of any other transformers. So there is actually a topological order between these transformers and estimators. Sorry, they do have a relationship, or you can actually draw a DAG of this stage. So the transformers and the order here should be the topological order on that DAG. Now let's look at this figure. So hopefully it will give you a better understanding of how a pipeline works. So this is when we have already defined the so-called build the pipeline. We have a word tokenizer, we have a count vector, a vectorizer, we have a string indexer, and a naive Bayes, which is an estimator. All right. So transformers are in a blue box, estimators are in red box. All right. This is what we have, a pipeline. And when we call pipeline.fit, the raw text or the raw data frame actually will act as the input of the pipeline. So it is actually act as the input of the pipeline.fit. It will go through the word tokenizer where you get the words. Then go through the count vectorizer, you will get the feature vectors or the count of these words as feature vectors. Go through the string indexer, you would get the numerical labels. And finally, it goes through the naive Bayes, the estimator. And the estimator will learn from the given feature vectors or features and the labels. So the features and the labels are fed into the naive Bayes model, and the output here would be a transformer. Right. So here, because for an estimator, essentially it does the similar thing. I mean, except it does not have this these transformers before itself. Means you can actually call this fit method on a estimator itself. It is essentially the same as the same in terms of how it works. I mean, the same as you call the fit method on a pipeline. So basically, just remember what you will have is a transformer. Right. And this is also known as the training phase. And also, I mean, in sklearn, they use the same name of the method as well, called. Now, after we have called pipeline.fit, we would have a pipeline model, right? And it is essentially a transformer or a list of transformers, right? So that's why you can call the transform method. And as you can see, the pipeline model are different from a pipeline as the last element, last stage here. Before it is an estimator, and now it becomes a transformer, which is generated by pipeline.fit. And also, the input of pipeline model.transform is the raw data frame. It goes through the word tokenizer, the count vectorizer, the string indexer, and finally it goes through the naive Bayes model and get the predictions. But remember, in this step, it only needs the feature vectors. It does not need the labels here. Right. So actually, we can put this stage out of this pipeline. Let's say we do it before the pipeline. We just convert the labels here into we convert the categories into integer labels, and then the pipeline would be only contains the word tokenizer, count vectorizer, and naive Bayes model. Right. So because here this step is kind of a waste of time. So in terms, so considering about the performance, we can take this stage out of the pipeline. So this is actually a bad design, example of the bad design of a pipeline. Right. Now a little bit more on pipeline. A transformer takes a data frame as input and produce an augmented data frame as output. We have been seeing this for a couple of times already. The examples are tokenizer and count vectorizer, as we explained before. So the data frame. So more specifically, for a transformer, you need to define or specify the input column and output column. So this is what it does. An estimator must be first fit on the input data frame to produce a model. And after fit, we get a transformer. Then we can use a transform to do the prediction. All right. So the example is a naive Bayes. So just remember, when you have a pipeline, you need to fit it first, and then call the transform method. All right. This is you have to do this even there is no estimator in the pipeline, and we will see why in this in the third bullet point. So pipelines and pipeline models help to ensure that training and test data go through identical feature processing steps. What does it mean? It means that, for example, when the test data contains word that is not in training data, it will not affect the generation of the feature vectors. In this case, this word that is not in training data will be ignored. That's why we say you must fit first, even there is no estimator. Even there is no estimator. Because if you don't fit, then you will generate different feature vectors for test and training data. And this is not just about whether you contain a new word or not. It will actually affect the feature vectors, affect the index of the words. For example, here, if you, let me see, let's see, we have a sentence, and this is, we have a sentence as training data, and this is what we have. And we also have a sentence in the testing data, which just has one more word that is happens to be new. I mean, not in the vocabulary of the training data. So if we don't fit and transform, if we just call transform on this testing data, then the features here would be different. It might be totally different. I mean, even for the same sentence, it could become, I don't know, I'm just write some numbers here. So even they are the same sentence, the feature vectors would be totally different. And when the feature vectors becomes totally different, means the distribution has changed as well, and means it is meaningless. You take this feature vector to a already trained classifier to do the prediction. Right. That's why even for a pipeline that contains only transformers, we need to fit first and then transform in order to keep or make sure the consistency between training data and test data. Now let's look at the code of train and evaluate the classifier. So basically, we have already built the pipeline. So we first fit the pipeline with, or we fit the train data into the pipeline. Then we got the model. So this step, we essentially train the classifier. And remember, in this step, the feature column and the label column are both contributes to this training stage. And then we can transform. So we use a development data to do the model transformation. Sorry, to do the transform. Then we get the result here. So in the transform step, we just get the prediction. So only the feature column contributes to the prediction, to the output of the model.transform. Right. And also, as you can see, as you can imagine, for the development data, it goes through the pipeline. So do the tokenization to get the number, the count vectors, or the feature vectors, and also convert or do the label indexer. All right. And we keep the labels. We keep the labels or the label column because we want to evaluate the performance of the classifier. So in this step, we initialize an evaluator. Right. So the evaluator, because here we consider a multi-class classification evaluator, right? And we need to define the prediction column. All right, the prediction column. which we have defined here. All right, which we have defined here. So as we have mentioned, the prediction result will be outputted to this MB prediction, to this column named MB prediction. All right. So we use this as the input parameter for prediction column. Actually, the label column is by default is a label, so we omit it here, but you can actually write it just in case you have a different column name, right? And the metric name, we use F1 as we have introduced before, right? We use F1 as the metric name here. So in order to evaluate the result, you just call evaluate, and the input is a data frame which is the result of a model.transform, right? So the development result is the input of the evaluate method, right? And well, you can print it to see the F1 score of your classifier on this development dataset. Now let's look at, let's go back and start from the very beginning of this example. Just remember all the, just have a look of all these things, because it might be used in your project too as well. At least the idea or the main procedures. So basically, you initialize, you create a Spark section, you read the data. You can use show to see how your data looks like, or print schema to print the schema of your data frame. We build a pipeline, right? We build a pipeline, and the orders matters here, and we fit the pipeline. We fit the train data to the pipeline in order to train the classifier, and we do the prediction using the trained classifier or the trained pipeline model using this transform method. So in order to train it, just to make sure either your pipeline contains how to convert into how to generate the feature vector, or the input data frame itself has the feature vector column. All right, and the output or the prediction column is defined here. All right. So this is essential. You need to define the features column, the labels column, and the prediction column. As you can imagine, if your data frame has multiple label column, for example, and multiple features column, also you can define multiple prediction columns. Then you can train different classifiers. Of course, you may need to build different pipelines. But when you do so, you need to think about what stages can put into one pipeline. For example, if you want to build two classifiers, you probably need to build two pipelines. But if they share the same if they share the same label, share the same feature vectors, you can actually build a feature vector. You can actually build a pipeline to generate the feature vectors, and this pipeline can be shared. Not the pipeline, the data frame with the generated feature vectors can be actually shared with the two classifiers. You don't need to do it again. Right. All right, so that is pretty much all for this example of using machine learning library to do naive Bayes. And in the project, we actually no, it's not here. In the project, we actually will use another two classifiers or machine learning method. One is SVM, support vector machine, and one is LR, logistic regression. So the way of using them, despite the essential idea or the principle are different, but the way that you're using them are basically the same as you call the function here. So you just replace it as SVM or LR. Although the name could be linear SVG, I guess, and a logistic regression. You will see the examples in Project 2's specification, so that won't be a problem. And due to the time limitation, it is not feasible for us to introduce more details about a specific machine learning model, because any of them requires a whole class, I guess, 2 hours at least, to go through and get everything clear. All right. So we won't introduce that. It's not the purpose of this course, but we will use that. So you just need to know how to call the function. But if you are interested, I mean, you can learn it by yourself or from other courses in CSE as well. So let's look at the second topic of today's lecture, which is Ansible learning. And it is directly related to Project 2, as in Project 2, we're going to implement the stacking method using MLlib and PySpark SQL. All right. So Ansible learning, the idea is that, or the motivation is that we want to use this to improve the machine learning results by combining several models. And it is actually effective because in many machine learning competitions, such as Kaggle competitions, you can see that Ansible method are usually placed in the first place. And the idea is more or less, I mean, if we use an analogy here, it's just like, when you do a group work, right? If you can cooperate it well, then usually you would be able to have a higher score than when you do it individually, right? Because when we have multiple contributors, it is easier to achieve a better performance. And in machine learning, it is the same, but the key is how to make use of them. Or say how to make them cooperated well, or improve the coherence between these participated models. Right. There are three major types of Ansible learning. They aim at different targets. For example, bagging aims at decrease the variance, the prediction variance. Right. Boosting is targeting at decrease the bias, and stacking aims at improve the prediction results. Right. And there are two groups based on how the base learners are generated. So base learners means, as you can imagine, Ansible learning. So the base learners is like the workers or the team members, right? And the base learners would contribute to the so-called meta learner or the team leader. So the team leader will organize the team and take the contribution from each and every base learners and use this to build or to make the final prediction, right? So based on how the base learners are generated, there are two groups of Ansible learning method. The first group is that when the base learners are generated sequentially, for example in AdaBoost, and the second group is when the base learners are generated parallelly. An example is a random forest, and also stacking is another example. So apparently, when talking about parallelly, it is naturally it naturally makes you think of like distributed systems or the distributed processing methods such as Hadoop and Spark, right? So that's why we introduce this topic and also use it as the project topic in this big data course, right? And also, I mean, again, due to the time limitation, we won't be able to go through all the different Ansible learning method. So we will focus on stacking. We will focus on stacking, and the project is about to implement a stacking method. All right. So the idea of stacking, or in a general fundamental introduction about stacking. So stacking is an Ansible learning technique that it combines multiple classification or regression models, also called base models. It combines these base models via a meta classifier or a meta regressor, which is called a meta model. Right. So you can think of there are a set of base models. Sorry. And they contribute to the meta model, and of course we will see how this actually works. So the base models are trained based on a complete training set, and it often consists of different learning algorithms. So these different learning algorithms could be different models, or same model with different say hyperparameters. Right. This is the base model, and the meta model. The meta model is trained on the outputs of the base models, and they actually use the outputs of the base models as features, and sometimes additional meta features are also used to further improve the performance. In the project, we will use the output of the base level models as features, or as the first part of the features. We will also make use a additional meta feature, which is simply the joint outputs, which is kind of the most the easiest meta feature. We will use that as an additional meta feature to further improve the performance. So this is the general idea of stacking. Now let's look at an example. So for Bayes models, you have KNN random forest and naive Bayes, and each of them has the prediction on this data set. These are the labels, and these are their predictions. All right. And as you can see, for a stacking classifier, it makes use of all these three Bayes classifiers, and it is about to, as you can see, it actually achieves a better performance from this figure. As you can see, the performance or in terms of accuracy of the stacking method is much higher than any of these Bayes classifiers. And from the figure, you can also see how it makes use of different Bayes classifiers. It actually take consideration of each and the result from each and every Bayes classifiers. This figure on the bottom right is irrelevant to our topics here, so you can just ignore it. Now let's have a break, and when we come back, we will discuss the detail of the stacking method, and everything we have discussed would be critical for project 2.